This lesson is all about something called resolution of forces, or resolving a force. So what we've been looking at previously is how forces that act on an object at angles to each other, such as at right angles or at angles that aren't right angles, they create one resultant force. And you can find out what that resultant force is by putting the forces top to tail and drawing the diagonal between them. Now, resolving a force just means to do this process backwards. It means if you start with a resultant force, to resolve it, what are the two components that created it in the first place? That's what resolving a force means, splitting it up into the two components which made it. So, for example, here is the resultant force. Hopefully, we are happy that these two arrows would represent the two original forces acting at a right angle that could have created this resultant force. This resultant is made by two different vectors, one that is horizontal and one that is vertical. Now, they're both at right angles to each other. And resolving that resultant force means finding the size of those two components. Now, this is all well and easy when you have a grid behind your force, behind your vector, because you can easily draw your horizontal and vertical components horizontal and vertical. And that can be really difficult when you are using plain paper. You also then need to figure out how long these sides need to be. The tops of the arrows that create the two red vectors here cannot be any longer than the top of the diagonal component here. Again, that's easy to do when you have a grid or a piece of graph paper to work with. Remember that these two vectors must be at right angles to each other. A common example to work with are resultant forces that act downwards like this. Now, don't let this fool you, don't let this trick you. Just because it's one force acting completely downwards doesn't mean that it can't be split up into two different components. So the components that could make up this one would look like this. Again, the tops of those arrows must join with the top of the diagonal, and those two arrows that the resultant has been resolved into have to be at right angles to each other. Again, quite simple when you're using grid paper or graph paper, quite difficult when you are using plain paper. So I'm going to show you how to do this using plain paper. So in a question, you could be told that you have a force, and I'm just going to draw any random force. I'm going to make mine be 5 centimeters long. So that could mean that that is 5 newtons. That is my one resultant vector. Now, in a question, you would probably be told at what angle your force is creating with the horizontal. So this is a horizontal line going straight across. If I put my protractor on the bottom of this line, then I can see that with the horizontal, this is making an angle of 30 degrees. Now, in your question, That is what it would tell you. Okay. Now, if I was to move this protractor slightly, I could say, oh, well, that angle might actually be at 40 degrees. That takes it slightly off center, my horizontal. So yes, I'm doing this as an approximation, but in a question, you would be told this. So I'm going to draw this horizontal line up. With my ruler. There we go. So I've done this going quite long. I don't know what length this has to be yet, but remember, we're assuming the question has told us that this angle is 30 degrees. So this will be my horizontal component. I just don't know how long this is going to be yet. Now I'm also going to have a vertical component. If this has to be a right angle in this corner here, and that's 30 degrees, then that means that the angle on the other side of this must be 60 degrees. They've got to add to be 90. So this has to be 60 degrees. So using my protractor again, I can put it back where it was, and the rest of this has to go up to 90. That has to be 60 degrees. And I can draw my vertical component in. So I have a vertical component, a horizontal component, and they are acting at 90 degrees to each other. But I don't know yet how long they need to be. The reason I'm not just drawing this in freehand is because I could make it go slightly off center or slightly off center. This has to be perfectly vertical to figure out how long this horizontal vector needs to be. To do that, you have to realize that this would also be a right angle. If that's a right angle and this is 30 degrees, then this must then be 60 degrees, because all three of them have to add up to be 180. So we've got 90, 30, 60. So then we can use our protractor again, and we have to make sure that this angle is perfectly 60 degrees. So there's my 60, which creates this angle, and then I can put in a little line on my protractor and then draw in this arrow. There we go. So as you can see, my little construction line, my dotted line, was a little bit off. That's why I did not draw this freehand. And now I can properly draw in my horizontal vector because I know how far it must go. It must reach this point here. If I measure that with a ruler, I can see that that is 4.4 newtons. Because it's 4.4 centimeters. Now you can do exactly the same with the vertical, because if this has to meet this side at a right angle, then this angle up here must then be 30 degrees. So you can draw your horizontal line in 30 degrees away from that bit there. However, some of you might have realised that this side is also going to be the same as this side. So you don't actually have to draw the next one in. Your vertical vector is going to be that side that we've already done. And so if I measure this, that is 2.5, 2.5 newtons. Now, if you want, you can check this. You can use Pythagoras to check. And again, I've told you this before, you will not be asked to use trigonometry or Pythagoras to check anything in an exam. This is more just for you to check for yourself if you want to. So we know that this side here, side A, is going to be equal to the square root of b squared plus c squared, which is these two. So we can have a look and see what that gets us. So 4.4 squared plus 2.5 squared, square rooted, gives me an answer in my calculator of 5.06. That is pretty spot on. So I've done that pretty well. Okay, now a real common example of where you could have to resolve a force into those components is looking at objects on a slope. So here's my slope, and here is an object. It's just going to be a box. Now you could be told in the question the weight of this box. So let's say, for example, that the weight is, oh, I don't know, let's go for 70 newtons. So not much at all. So I know that weight has to act vertically downwards. Okay, again, I'm not going to draw this in first of all, because I don't know yet how I can make that be a complete vertical line. But what you could be told in a question is the angle of your slope. So I'm going to say that the angle of this slope, and again, I'm just going to do this as best as I can with what I've already got. I'm going to say that the angle of this slope is going to be 33 degrees. If this is 33, just like we did up here, we have our weight acting down, then this angle up here has got to be 90, take away 33, which is 57. So using my protractor, I can now, from a point on this box, make sure that this angle is 57 degrees. So there's 50, 5, 6, 7. So now I can make that my weight connecting with this. If it's 70 newtons, I might want to make this be 7 centimeters. So there is my weight of 70 newtons. Now this weight can be split up again into a horizontal and a vertical component. So my slope is actually already starting off this horizontal component. So I already know that's 57 degrees to my slope. So my horizontal component has to be some length of this line. Now we've got angles 57. If I need to make my vertical meet here at a right angle, then the angle down here must then be 33. It's all about our triangles. So taking my protractor yet again and pop it here. There's 30. 1, 2, 3 comes to here. make sure that it goes through there. And there you can see here, it's my horizontal component. And here is my vertical component. I don't need to draw the rest in. I could, but I don't need to. So I could make this angle 33. I'd know that this angle would have to be 57 and use my protractor to draw this accurately. I could, but I don't need to because this side is going to be the same length as this side. So just as I used a cheat up here, and I said that this side was the same length as this side, you can do the same with the one that I've just done on the bottom.